Good morning, everyone. In a couple minutes, we're going to do a demo. Just so you know, we're going to do our favorite pumpkin demo. We'll start it in a couple minutes. A few of you guys are wearing costumes. I'm kind of, my costume's hidden right now. So I thought I would reveal my costume, which is, I'm cloudy with the chance of showers. So yay. Yay for me. And also cloudy with the chance of meatballs, too. I don't know. If anybody wants a meatball, let me know. But after they do the demo during class, if you want to come grab candy, feel free. Or at the end of class, feel free to grab candy. I think in a minute I'm going to take this off because it's kind of silly. But our demonstration staff's going to do a pumpkin demo. They're going to get that started in just a moment. And the way I like to kick this demo off with is we're going to try to carve that pumpkin using chemistry. You can probably see it's pre-carved, but I always like, when I do this demo, I always say it's really hard to get the pieces of the pumpkin out. So why don't we use chemistry to help us finish carving the pumpkin? So they're going to get started on that in just a moment. But I hope you guys have a good Halloween. And awesome for the people in the room wearing costumes. See a couple costumes.
Feel free to dim the lights.
Oh, yeah. So what we're going to do here is we're adding calcium carbide to water, which is going to make acetylene. And then when we provide a spark, it's going to light the acetylene, cause a combustion reaction to take place, and then hopefully we get a nice kaboom.
Right. And you guys might want to cover your ears like this.
Yeah, it's not as loud as like the balloon. Like, I'm not worried.
So here's a calcium carbide, and there's a tuna can with about 90 milliliters of water in it. It's a pumpkin.
It's going to be a couple minutes, or not a couple minutes, 30 seconds or so before we go kaboom.
So right now the acetylene gas is building up inside the pumpkin. A few more seconds.
Yay. Clap, 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 clap. Thank you, guys. That was awesome. Oh, thank you. My wife gave me the idea. I was thinking all week of something silly to do. Something. All right, so I think I got that recorded for those not here, or if you just came in and missed our pumpkin demo or seeing it on the way in. We were just carving the pumpkin using chemistry. I like to mention calcium carbide is actually CaC2. Like, we don't talk about the carbide ion too much, but that's an ion of two carbons bonded together with an overall 2- charge. And then also, if you're just coming in, I was cloudy with a chance of showers with my little spray ball of water. So again, hope you guys have a great Halloween this weekend, and have some awesome costumes planned for parties tonight and over the weekend, and then you don't get into too much trouble. At some point in class or after class, grab some candy if you haven't yet, or if you just want another piece. But anyways, we'll get back into our last problem from chapter 7 was this one here, which is talking about, or is getting at electrons in which subshell of the zinc atom experience the lowest overall effective nuclear charge. And so one of the things I wanted to do for the zinc atom, and in general we can do this for essentially any atom. We should be able to go through and just kind of rank order which electrons experience the greatest nuclear charge and which experience then therefore the lowest nuclear charge. So we know in terms of the total electron configuration of zinc, if we start all the way from the 1s, that it would be a 1s2, 2s2, 2p6, 3s2, 3p6. So that gets us all the way across to argon. And then from there we go 4s2, and then into that 3d. And zinc is all the way across the very end of the D subshell, so it's a D10. like we could ask maybe the valence count once you fill that D shell. We would probably say you just have these 2 valence electrons. Spotting the valence electrons is sometimes useful just so that you can know that these are the outermost and these are the important electrons in terms of the bonding of zinc. If we know that those are the only 2 valence electrons, then we might have a pretty good idea that they should probably be the ones that experience the overall lowest effective charge. That's why they're going to be the electrons that are removed upon ionization to zinc 2+. So if we're thinking the overall effective nuclear charge that these subshells experience, it's actually not the order that we wrote. It's actually not 4s then 3d. The overall order would just go 1s experiences a greater effective charge. So like how much of the nuclear charge does the 1s subshell experience? The 1s subshell is experiencing almost the entire nuclear charge. It gets to see the full plus just about, maybe a smidge below. If you remember the one curve for argon, and one of our earlier slides showed that it experiences or has a nuclear charge of 18, and if you read off the apparent nuclear charge the 1s of that atom absorbs, it's probably like 17.5. So the other electrons are fighting for some of that space close to the nucleus because each of the subshells does have some probability of being relatively close to the nucleus, and so that's what we're kind of getting at, that each of the subshells has a little bit of a probability, but the 1s has the most probability of being right on top of the nucleus. Then it goes the entire 2s subshell, experiences a greater charge. Then it's the entire n equals 3 subshell. So we go through the entire n equals 3 subshell from 3s to 3p to 3d. Then the only main question might come down to, then why did we fill the 4s before the 3d? Like why did potassium and calcium go 4s1, 4s2 before filling the 3d? It just becomes a give and a take. Do we want to experience a greater charge and then have greater repulsion with the other electrons, or do we want to go further away? So potassium, calcium, for whatever reason, said, well, let's just put our electrons further away so we don't have as much electron repulsion. But then once you up the nuclear charge and you go across adding 1 to 10 more protons in the nucleus as you go from scandium on across the zinc, zinc says, all right, we're going to fill those next 10 electrons into the area that's closer to the nucleus where they experience a greater effective charge, and then our 4s comes next. So we go through the entire n equals 4 shell before we would get to the effective charge of the n equals 5 shell. And the same thing, we went through the entire n equals 2 shell, and then all the n equals 1 shell with just the 1 subshell. So we're going through all the n equals 1, then the 2, then the 3. So what that means is that the n equals 4 subshell being the furthest away, it's like the largest. This also corresponds to the size of those subshells on average, that the 4s is the larger subshell compared to the 3d. So even though we believed, or the way we write our configurations is thinking about filling the 4s first, the 3d is actually closer to the nucleus, experiences therefore a greater amount of charge off the nucleus, making it harder to remove those electrons. And so that's the explanation on why zinc 2+ would form a configuration that would be, the argon configuration followed by a 3d10. And then with that 3d10 configuration where we've lost, for zinc 2+, we've lost these 2 electrons, the outer valence electrons. So again, if we knew the valence electron rule, we'd probably be like, well, we're probably going to lose the 2 valence electrons to ionize zinc to zinc 2+. And then we leave behind that D subshell where we should have all those electrons spin paired. The spin paired question, the reason why we might ask you for how many unpaired electrons does the zinc cation have is to kind of make sure you have the right configuration. It's like a way of asking about the configuration without asking for the configuration. And that's also the way we as chemists can check configurations. We can very easily do experiments to see how many unpaired electrons does an ion have, and we can determine those very easily. We can see for zinc it has 0 experimentally, and then our configuration shows that it would have 0 as well. So the electrons in the 4s subshell experience the overall lowest effective charge, and then we have 0 unpaired electrons for zinc. So this is a question that gets at electron configurations for cations, and we're losing the electrons in order of the largest electrons first, and the largest electrons have the highest n with the highest L. So the highest n here is 4, so we lose those electrons first. If we were going to make zinc 4+, which turns out not to really be common or likely, but then we'd start taking from the 3d. So if we lose 2 more electrons, those are going to come out of the 3d subshell. So just one more thing I wanted to mention from chapter 7 was something I meant to mention earlier about hydrogen. So one of the things that's interesting about hydrogen compared to the other or the alkali metals is the difference of its ionization energy. So you can see hydrogen here has an off-the-chart ionization energy. So that's one explanation for why hydrogen's a little bit different from lithium, sodium on downward, is that the ionization energy for the alkali metals is very, very low. Hydrogen's very, very high. Hydrogen just holds onto that electron much more strongly. It can release it. It takes 1,312 kJs per mole, and hydrogen will form H+. So it's not that it's impossible for hydrogen to form H+, it just takes a lot more energy. So what that means is hydrogen really wants to keep a hold of its electron, maybe share it with another atom, make an H2 molecule, maybe share it with oxygen, make a covalent bond between H and O, and then it could possibly absorb an electron. We know it's possible to make H minus, so we can make the hydride ion, we can make H+. It's just going to take such a great amount of energy that we're going to then lead to a different type of structure. We're going to lead to hydrogen not existing as a metal. Metals generally have low ionization energy so that they can share valence electrons with each other. So what sodium and lithium are doing is they're taking their extra valence electron and almost sharing it across the entire structure of the metal. It's hard to picture how that is. We'll talk about that a little bit more in chapter 12, but I just wanted to show that hydrogen is definitely off the chart. And I also wanted to mention that if you think of the Bohr model, you can actually calculate the ionization energy of hydrogen very accurately. If you were to take like the energy of n equals 1 and use the Bohr model, remember energy is a function of n just for hydrogen, is that it's negative 2.18 times 10 to the minus 18 joules, and then 1 over the n value squared. So if I'm calculating the delta E for H plus minus H in the ground state, this is n equals 1, this is n approaches infinity. So as n approaches infinity, we're dividing by a larger and larger number. So this would be equal to a number that approaches 0 and then minus negative 2.18 times 10 to the minus 18 joules. But that's per atom. If I were to take 2.18 times 10 to the minus 18 joules and just multiply that by Avogadro's number, let me do that real quick. So if I take the negative of negative 2.18, that'd be plus, so 2.18 times 10 to the minus 18 times Avogadro's number, that would be the number of joules. For the ionization energy, if I divide that by 1,000, I get 1,300, I actually get 1,313, so I'm probably rounding something off, but I get that number. So I get that ionization energy of hydrogen right from the Bohr model. So it follows from the Bohr model that we can actually calculate for H, its ionization energy. We can see it's very high, much higher than the other members in its row, so it behaves a lot differently, exists as a gas as opposed to a metal like lithium and below. This also shows that most of our nonmetals have relatively high ionization energies. A lot of them have relatively low or favorable electron affinity, so they can absorb electrons in favorable steps. Okay, so I just wanted to point that out before we head into chapter 8. So with that, let's take a look back at kind of our roadmap for chapters 6 through 9. That chapter 6 is looking at properties of the electron. Chapter 7, nuclear trends of the from left to right. And then chapter 8, we're going to finally get into some properties of bonding and ionic and covalent compounds. So we're going to talk mostly today about ionic compounds. Then for the rest of chapter 8, Monday on forward, we'll talk a lot about covalent bonding and compounds. We'll talk about polarity. We'll talk about Lewis structures, how we can sketch them, and how we can think about the type of bonds and lone pairs that molecular compounds have. And then chapter 9, we'll get into the three-dimensional shapes of those molecules. So the actual representations and the shapes of molecules will follow into chapter 9. Hello, the next few slides are going to be a re-record from today's lecture because I forgot to hit the record button until about halfway through lecture. So chapter 8, we're going to talk about concepts of chemical bonding. We're going to talk about Lewis symbols and the octet rule. Some atoms can follow the octet rule, those mainly being in the second row and beyond, and those usually being in the main group. The S and P block elements will most likely follow the octet rule. Hydrogen and helium really can't. They're not going to get to 8 electrons around them. But we'll talk about the octet rule, what it is, how we use it here in this chapter as we proceed. We'll talk about ionic bonding and lattice energies to describe ionic compounds. And then for the rest of the chapter, focus on covalent bonding, polarity, electronegativity, and then drawing Lewis structures for all kinds of compounds, and then talking about resonance, compounds that violate the octet rule, and then get into lengths and strengths of single, double, triple bonds. We'll talk about those a little bit today too. So there's 3 main types of bonds that we see in chemistry. We have the ionic bond. That's what we're talking about here in this chapter, and also covalent bonding in this chapter. And so those are the cases where ionic bonds involve the donation and accepting of electrons, creating charges, and then the electrostatic force of attraction of those ions once they're formed. Covalent bonds tend to form between atoms that have too high of an ionization energy, not maybe as favorable electron affinities putting it all together, so they have to share electrons instead of creating plus and minus charged ions. So we see these a lot between nonmetallic elements. And then if you look at just metals together, they tend to form a type of bond together we don't talk about a whole lot, but the metallic bonds are held together by a lot of times what we call the sea of electron bonding. And what that means is that the valence electron or electrons of one atom just exchange with the other atoms, and the electrons flow through the structure as if they really don't belong to any of the ions. So if you think of bonding of metals as being, instead of electrons being either here or here and it being ionic or it being a shared, it's all the electrons are always being shared. So you put a charge, so say you put a positive charge here, all the electrons can very quickly flow towards the charge. Put a negative charge, they quickly flow away, so you can get the conductance of metals understood through metallic bonding. We'll talk more about the nature of bonding within solids as we get into a discussion of the bonds within liquids in chapter 7 and then within solids in chapter 8. So let's talk about Lewis symbols and the octet rule. So if we're writing a Lewis structure of something like lithium, we're just writing the one valence electron in. So we fill in the Lewis symbol with the valence electrons. So beryllium has 2 valence electrons. Now it's perfectly legal and allowed to write the Lewis symbol of beryllium with 2 dots as opposed to a dot on either side. So you can go this way or this way, that's fine. For boron, you could write 2 together and then the third. You could write the 2 together here and the one on top. So it doesn't matter really where you're putting these dots other than not putting generally 3 on a face. So we generally don't put 3 dots on the face of an atom, generally 2 max. Not a big deal there. Carbon, we could write 4 dots for its 4 valence electrons like this, or we could instead write 2 dots together, then 2 on either side. So another way of writing carbon might be 2 dots together, and then a 1 and a 1. We can write our dot structures as just showing the valence electron counts for the atoms. Nitrogen 5, oxygen 6, fluorine 7, neon 8. And you're just filling in that shell of electrons, completing it with a noble gas, and then we can understand that fluorine's going to make F minus by absorbing an electron in to come up with that same neon configuration. Oxygen goes to get its noble gas configuration would be at a 2 minus, etc. If we go to nitrogen, let's just continue here to a 3 minus. Now, carbon probably won't do this very often, so a 4 minus, this isn't really likely to form. We did a demo today with carbide ion, which is actually this ion here. Don't worry about sketching the Lewis structure just yet, but it's the C2 2 minus ion. So this turns out to be the carbide ion that we talk about and not the C4 minus ion. Now the issue with even nitride not being so common is that as you go from fluoride to oxide, it's taking more and more energy to add more electrons to something like nitrogen. So from nitrogen, go from the N atom to N3 minus. There's a fair bit of energy that nitrogen has to absorb in order to add in 3 electrons to its shell. If you think of carbon, it's going to be even more energy. So it's just not as likely to make these ions as you get into the middle parts of the periodic table. It's going to be easiest the closer you already are to the noble gas counts. Being smaller is better towards that high effective charge. So this is why predominantly we're seeing, like ions forming, like nitrogen, oxygen, fluorine, sulfur, chlorine, bromine, iodine. So where we're close to that noble gas configuration, so that we can come up with that configuration that quote unquote is more stable, but stability is a tricky thing. A lot of those configurations don't really in and of themselves give off enough energy. Like when we look at, for example, sodium plus chlorine, it's an explosive reaction, highly exothermic reaction to produce NaCl. But the question is, well, where does that exothermicity come from? It doesn't come just from the sodium reacting. In fact, maybe the next slide I'll get into this a little bit more. But it's not just from sodium forming the plus and the chlorine forming the minus. It's then the electrostatic attraction once they form. So here our ionic bonds are forming for our metals. Low ionization energies are non-metals. On the right side, the most favorable electron affinities. Sodium loses an electron to make sodium plus. That reaction there, sodium as a gas going to sodium plus an electron. This is 496 kJs per mole positive from our ionization energy we saw in chapter 7. And so absorbing the electron in by chlorine to go to Cl minus, you might think, oh, okay, that's good, but it only gets you back 349. And then even from there, to get sodium gas from sodium solid takes energy. To get chlorine gas from Cl2 takes energy. The chlorine bond strength is like 242 kJs per mole. Sodium solid has to absorb energy to form sodium gas. It takes energy to create these ions. Where does the exothermic nature of this reaction come from? It comes from then once they form, you get this attractive force. You get that kappa Q1, Q2 divide by D. So you get the Q1, Q2 divide by D energy coming back off once those ions form that electrostatic force of attraction. So it's once the ions form, then this takes place. Then we have sodium plus Cl minus forms sodium solid. And then this reaction here is about a delta H of minus 800 kJs per mole, approximately. We'll see on the next slide that a little bit more detailed. So this slide here is showing us that lattice energy calculation, the energy that must be absorbed to separate a solid ionic compound into its gaseous ions. It's considered to be a measure of ionic bond strength. And so if we take a look at sodium solid and Cl2 here, this is elemental sodium, elemental chlorine. Those are the most stable forms of those elements at room temperature. If we want to break the attractive force of sodium solid to the gas, we have to have energy absorbed in. So energy is going upward here on the vertical axis. So sodium has to absorb energy to form sodium gas. Chlorine has to absorb energy to break its bond to form chlorine atom. That takes energy. That's energy in, not energy out. We ionize sodium. You might think the sodium plus, the neon configuration of sodium is more stable. Well, it's really not. It takes energy to create sodium plus. We don't get energy back. When we think of something being more stable, that would usually mean we get energy out of the process, but it's endothermic, not exothermic. And then when you think, oh, okay, we'll get the energy back when we put the electron on chlorine, but we only get some of that energy back. We're still way up here in terms of net energy. So if we were just forming gaseous ions and they were going to float away into the ether, well, this isn't going to work. That's not exothermic. They would just revert back to the reactants if that were the case. But instead, what if those ions pair together and then you end up solidifying a lattice? You end up making NaCl where you get the plus minus, plus minus, plus minus replicating itself throughout the structure of the solid. This is where you get that stability of sodium chloride and why it forms and predominates from the reaction of sodium and chlorine. This is minus 788 kJs per mole. Now this number 788 here is calculated by precisely knowing how much up here, how much up here, how much energy is this, how much do we get back, and then what's the difference of the delta HF of sodium chloride. So you can solve for this number using a Hess's law cycle. I'll mention towards the end of class. There's some problems in the handouts on calculating the lattice energy. I don't know if the goal is to necessarily have you understand that we don't directly study a lattice energy, but we indirectly study it through knowing all the other reactions underlying our picture here. But the key is that it is why the compound NaCl forms. It forms because it's more stable. Sodium chloride is more stable than its elements. It's this difference here from the elements is more stable. So we're going to have a hard time forming compounds that are less stable than their elements. We also should talk about stability in the form of free energy and not necessarily just the delta H. So if you're sitting there thinking, well, wait a minute, isn't it supposed to be the delta G should be more stable? Yes, that's true. We haven't talked about that yet. You'll learn about that in chapter 19, but the Gibbs energy of NaCl is more stable than its elements. Therefore, sodium chloride is what we find in nature, not the elements sodium and chlorine. If they're introduced together, they'll react to produce this compound. In the compound forms, largely due to the fact that we take the sodium gas, chlorine gas, combine them to form the solid, and that's where we get the attractive force between the plus and the minus ions, that electrostatic force of attraction. Make sure to note that the lattice energy forms gaseous ions from solid ionic compound, so that we just get a measure of this ionic bond strength. Some lattice energy trends. If you look at our equation for the energy of electrostatic attraction, we know this equation is negative when we have a plus minus or a minus plus. So think about the magnitude of the electrostatic force of attraction here. So think about what's going to make the magnitude of attraction bigger or smaller. What makes the magnitude of the attractive force stronger is going to be the magnitudes of charge being as high as possible, or the ions being as small as possible. So smaller ions makes kappa Q1, Q2 divided by a smaller number, makes the energy of attractive force go up. So notice that the lattice energy is this, these are all plus minuses. Let's make sure we know what we're looking at. So these are all plus one, minus ones. Our lattice energy is the greatest for the smallest pairing of the ions, LiCl. Make lithium larger, you reduce the lattice energy. So make the distance of separation now go up instead, then you're going to then reduce the energy of electrostatic attraction. So you have this inverse relationship to the distance of separation. The distance of separation is related to the size of the ions. So the D increases as the size of the ions increases. So make the size of the ions bigger, then D goes up. Make the ions go up, then the energy of attraction goes down. So imagine that you have a positive charge here and a negative charge here. That's good. If you have a positive charge here, that's now much larger. So if instead we're picturing having a huge positive charge and the same minus charge, then the positive charge is further away from the negative. It's weaker, easier to break the attractive force. Same thing happens if you change the charge of the ion. So these are all minuses and pluses. So plus one, minus ones. For the case of sodium fluoride, chloride, bromide, iodide, the bigger iodide, weaker, smaller fluoride, stronger. So higher lattice energy takes more energy to separate sodium fluoride than it does sodium iodide. This page here is showing us over here some more trends for some other compounds that allow you to compare the increasing size, the decrease in the lattice energy, but it allows us to look at the charge magnitude. So let's start with scandium nitride. So scandium nitride is scandium 3 plus, nitrogen 3 minus. So we've increased the magnitude of the charges here by a factor of 9, and roughly our lattice energy is about 9 times higher than they were for our plus one, minus one. So a big difference in lattice energy for scandium nitride. Now, just to be clear, this would be the energy for forming scandium 3 plus as a gas, and then plus nitrogen 3 minus as a gas. And so the lattice energy for that compound a lot higher due to the fact that the magnitudes of charge are higher. So you increase the magnitudes of charge, then you increase the magnitude of the electrostatic force of attraction. If you go plus 2, minus 2, it's not as much as scandium nitride, but it's higher than the plus 1, minus 1s because we've increased the magnitudes of charge by about a factor of 4. Then make magnesium larger, and larger again, you reduce the lattice energy due to then the distance term. So you can see D still plays a role, that as you go to larger ions, you separate them by more and you weaken their attraction. Same thing with magnesium 2 plus chloride minus. So see the same trend here, but just not as high because the magnitude of one of the ions isn't as highly charged. So you're seeing a lower lattice energy resulting for magnesium chloride. Technically, magnesium chloride goes to breaks 2 bonds. So the ionic bond strength here for the magnesium chloride bond, those being gaseous ions, I won't write the G in, but the ionic bond strength here is divided by 2. So the ionic bond strength for the 2 plus minus is about 1,200 or so kJs per mole. For the 2 plus 2 minus, it's about 3,200 or so kJs per mole, and then it's about 7,200 plus kJs per mole for the plus 3, minus 3. So there's a big impact of charge on the lattice energy. There's a smaller impact that the size makes. So the size is making a smaller difference. So the charge trend makes a big difference in lattice energy. The size trend generally a little bit of a smaller difference of impact on the lattice energy. But that actually takes us through the ionic bond. So I actually got through maybe a little quicker than I thought, ionic bonding. So ionic bonds can just be described by how highly charged the ions are. The higher the charge, the stronger the ionic bond. And then how small the ions are, the smaller the ions, the stronger the lattice energy, the stronger that ionic bond is. Well, let's get into covalent bonds, because this is really going to be where we focus our attention on for the next couple weeks. Chapter 9 will study a lot of covalent bonds in terms of their three-dimensional shapes. We need to know a lot about the nature of covalent bonds, so let's get a look here. So covalent bonding is where you have electrons that are being exchanged through or shared by two nuclei. So one picture is just, we have two electrons being shared. These electrons are being shown as discrete particles, which probably isn't good. We think of electrons more by a probability distribution. So this is showing us here what like a probability distribution might look like for perhaps hydrogen. So imagine we have the H2 bond is what we're looking at here for the electrons being shared across that single bond between two H atoms. If we were constructing the Lewis structure, really simple, connecting the two unpaired electrons of hydrogen and then pairing them together into a bond. We'll see when we get to like a bonding theory that you can imagine the spins of those electrons pairing up into that bonding orbital, so the electrons kind of pair their spins together, and then they're most probably found somewhere in between the two nuclei. And then on average, one of the electrons is closer to the one nuclei, the other is closer to the other. So there's no net charge building up on hydrogen in this calculation. We'll have a calculation throughout chapters 8 and 9 on like formal charge. Is there a formal charge developing on hydrogen in this structure? The answer would be no. We'll see a bunch of examples of this, but when I'm thinking of, does the atom bear some kind of charge in my Lewis structure, it's going to be a thought of, well, how many electrons on average, if I break this bond in half and just consider one electron is closer to one atom, the other is closer to the other, what's the net charge in each of the atoms? Well, hydrogen should have one electron for a neutral charge. It has one electron closest to it, so it's neutral. We'll see this calculation a bunch of times. There's an equation for it. I'm not a big fan of the equation because I forget equations, but it's just thinking, well, how many electrons should hydrogen have versus how many does it have within that Lewis structure? And then if it's the same, then it's uncharged. And it's always a balance of, there's one proton in the nucleus of hydrogen total, so one electron total, that balances out to a neutral charge. So a lot of ways you can think about charge. It's just the nuclear charge balance versus the electron count balance, or it's the valence count balance versus how many valence electrons around the atom within the Lewis structure. Another picture of bonding, this comes out of chapter 9. I don't know why they say this picture for chapter 9, because it kind of shows us the picture of bonding that makes sense even from chapter 5. We know the hydrogen bond is endothermic. Any bond is endothermic, meaning it takes energy to break the bond. And so we even know, if you look back at the chart from chapter 5, that if this is H2, that this difference here is about 436, if I remember correctly, 432 or 436 kJs per mole. Not worth memorizing, but it's about 400 kJs per mole. It's good to kind of see just that it's about half of our standard +1 -1 bond. So it's weaker overall than our ionic bond, but just corresponds to hydrogen having some ideal bond distance. Turns out to be about 0.74 angstrom. If you compress the bond, the energy goes back up beyond its ideal bond distance. So every bond is going to have its best bond length that makes its nuclei happy, because you have two charged nuclei that repel each other. You have electrons that repel each other. But then the key is that these electrons have the attractive force with the nuclei. That's why this bond is forming, is each of those electrons has the mutual attractive force with the two nuclei. And that's why the bond is forming. But if we keep compressing, then all of a sudden you get too much electron repulsion, the nuclei repel each other, the energy goes up over here, so the potential energy goes up if we compress the bond too much. Then if we try to break the bond, then we're going to release the energy that that bond was holding on to, the stability that the bond had by forming, if we start stretching the atom away from each other and breaking that bond. So that's our basic picture of covalent bonding. It's shared electron pairs through this covalent bonding. Let's try to sketch Lewis structures, but from the picture of just like almost like connecting dots. Some Lewis structures are easy this way, some aren't. The ones that are easy are usually recognizable molecules. And what I mean by this is if we are picturing Lewis dot structures of these atoms, we can usually make our simple diatomic molecules like H2Cl2, the things like HF, water, ammonia, etc. And so what this is, just like the H2 example, we know hydrogen each has a lone pair, we pair them together. If I do HF next, fluorine, if I pair it up with 7 valence electrons, then we just pair up and make that single bond. So what we're trying to do here is in total give the atoms an octet, but through the sharing of electrons. In the case of hydrogen, its quote unquote octet would be the helium configuration. So each of the hydrogen atoms has 2 electrons surrounding it. So it's like you consider the full electrons from the shared electrons plus the lone pairs to see if you have 8 electrons around an atom, to see if you satisfied or if you're kind of getting towards what we think of as the octet or the stable configuration. And then if you're thinking of the net charge, you break the bond in half. So if you're thinking formal charge, which we don't necessarily have to think formal charge in every Lewis structure, but if we wanted to connect the idea of charge, all of these atoms here are going to end up uncharged in all of these molecules on this page here. It doesn't have to be the case in any Lewis structure that all the atoms are uncharged, but I know in all these simple ones, we're going to have a perfect sharing of electrons because we're just going to take atom 1 with its valence count, atom 2 with its valence count, share some electron pairs. So we're not really moving electrons around and exchanging them on the atoms in this process for these simple molecules. So we still end up with net neutral formal charged atoms. So these are the formal charges that we might write here. So the formal charges are just assume perfect covalent bonding, assume the electron pairs are perfectly shared, and calculate the charges. If I go to Cl2, I just orient the lone pairs at each other, so I can easily connect the dots and give each chlorine 8 electrons in its octet. And then and again, I haven't taken any of the valence from one atom and moved them to the other, which is what would be required to change the charge, because if I just break this bond back in half, my net charge is still neutral and neutral. So do you see how it would take me physically moving like a valence from one atom to another in order to change the charge? So there's going to be no way that any of these molecules, unless I start moving electrons around, that I can create atoms with a different charge. So for more complicated Lewis structures, I'm going to come up with a different type of rule. We're going to see a rule later for trickier Lewis structures where we don't necessarily start with atoms with their given Lewis dot structures. If we're not starting with a Lewis dot structure, then we really have to be more mindful of what the formal charges are. When I start with oxygen, let me start with oxygen like this, 2 lone pairs. So like a 2s2, 2p4. So you can kind of see maybe that's the 2s, that's a 2p spin paired. Then I have my other 2p2s. And then they're going to pair up with hydrogen with a lone pair to make water. Now, we try not to get too much into the actual nature of bonding here. The molecules really, these electron pairs are not flat-centered. Molecules are going to have a 3-dimensional shape about them. We're going to talk about 3D shapes in the next chapter. You could have written water this way too. If you put the 2 here, the 2 here, and the dots here, if you wrote it this way, you can write the Lewis structure either way. There's no rule that says you have to write Lewis structures linear or bent or in some sort of a way. Water turns out to have a bent molecular bond, so it'll look more closely to this, but this is still an okay way to write. There's nothing illegal about writing that Lewis structure. Now, the thing that you want to be mindful of is when you're writing a Lewis structure, just because you chose to write it this way doesn't mean that water has a perfectly linear bond. So just remember, when you're writing a Lewis structure, you don't compel the molecule to exist in the way that you write the Lewis structure. Even when you write a Lewis structure, you're not really forcing the atoms to do what you write. We're just trying to understand how can we break up and understand the bonding in a molecule like water. What we're really trying to get with a Lewis structure is, do we expect water to have single bonds or double bonds? We see here just single bonds. We haven't gotten yet to an example that needs double or triple bonds. We're going to get to them soon with N2 and O2. But it kind of the whole point of a Lewis structure at first is just to see where the lone pairs. Do I have single bonds? Do I have double bonds? Is there charge being exchanged anywhere within the structure? Then the next chapter we'll start to think, now how does this thing look in 3-dimensional space? NH3 and CH4, much like ammonia. So NH3, if we're picturing this dot structure, which I think is really the only really realistic dot structure for NH3. We just paired up the dots here to make NH3 with 3 single bonds. So all these atoms still net formal charges of 0. I haven't moved any electrons around. If you break the bonds in half, we still have 5 valence electrons around N, still 1 around each of the H's. So our formal charges still have to be neutral for all these molecules that we've written so far here. CH4, 4 dots is a good structure here just to give us our 4 bonds. So we get 4 single bonds for CH4. That's easy enough. So 4 single bonds, still net neutral across the board. N2 and O2, we can very, I think, easily then see with our dot structure how we end up with double bond for O2 and a triple for N2. Let's do nitrogen first. So let's point the dots more closely at each other. So we can pair up 1, pair up 2, pair up 3. So there's making the triple bond for nitrogen. So the probably easier way we write that is like this. And still, even though we're making 3 bonds, we're still net neutral. So if we break the bond in half, nitrogen is still neutral on either side. We haven't created an imbalance of charge in the structure, so that's good. And then if we do this for oxygen, then we just make a double bond. So we might write the double bond here, 2 lone pairs on each of the O's. Probably the most fascinating molecule is oxygen. Oxygen actually doesn't look much like this at all. Well, it does in a way. It really does have a double bond, but it actually has unpaired electrons. If we're thinking spin paired electrons, usually we write 2 electrons together, they're spin paired. Oxygen has unpaired electrons. It actually gives it a lot of its properties by it having those unpaired electrons. Most neutral molecules that are stable don't have unpaired electrons. And so a lot of the interactions oxygen has, like with hemoglobin, probably wouldn't have that without the unpaired electrons that it has. So we'll need a bonding model deep into chapter 9 to get out why oxygen actually has unpaired electrons. So we'll stop for O2. This is a good enough structure for now, but we'll see later that it actually has a little bit more of a complicated structure than maybe that Lewis structure is showing us. But Lewis structures are meant to show us the net charge of the atoms, the bonding type, double bond for oxygen, triple for nitrogen. Still uncharged, of course, so still neutral across our nitrogen and oxygens within N2 and O2. This is showing us then what about CO2 versus, for CO2, you're going to connect and make double bonds. So you make 2 double bonds on either side of the atom. So we're making 2 double bonds between carbon and the oxygens. Maybe a better way to draw it is let's make 1 here, 1 there, 1 here, 1 there. So we're just making CO2, 2 double bonds. Still neutral across the board. We haven't moved electrons around yet, so we're still neutral in terms of our formal charges. Carbon has 4 electrons still closest to it if we break the bonds in half. Oxygen still has 6. Double bonds on either side. This slide here is then showing you, well, what about the difference between single, double, triple in terms of bond length? We'll see this also towards the end of the chapter, focuses on this as well. But we see nitrogen, if you only had a single bond, the bond would be longer, 1.47 angstrom. Nitrogen with a double bond would be shorter. Nitrogen and N2, really short bond because of the triple bond. As you add electrons to 2 nuclei, you're shortening the bond. So the electrons are like glue. So electrons are holding the nuclei together. Now, N2 wouldn't exist with a single bond outside of some other type of molecule. So in some type of molecule where 2 nitrogens have a single bond, I'm going to sketch in a molecule. You don't have to worry too much about this right now. But if you had a molecule like N2H4, it would look something like this. Then it would have a single bond. If you had a molecule like, I think it's called hydrazine, but if you had 2 hydrogens, 1 on each of the ends, it's still a lone pair on nitrogen, then you would have a structure that has a double bond. And then obviously if you had N2 with no hydrogens, you would have a triple bond. So the idea would be within the N2H4 molecule, single bond, longest bond. And so we get this bond length comparison. Fewer electron pairs are lengthening the bond. And then also you can think the triple bond is going to be stronger. By having N2 with the triple bond, that bond should be stronger. So our bond's going to be stronger here with the triple. We'll come back to that at the end of chapter 8. Let's just end here with our quiz today. I think we've seen a good amount of learning for today. Our word for today is yttrium, element number 39. So yeah, once you mark your quiz, feel free to take off and have a great Halloween. Thank you guys. Get some candy, there's a little bit left up here if you haven't gotten any.